Excellent.
Okay, thank you very much for inviting me to participate to this program. And what I would like to present you today is an analysis of the ability of a stochastic reduced model to reproduce the dynamics of a reference system, and I will investigate that in the context of a low-order ocean atmosphere system. But let me first introduce the problem. As you certainly know, the atmosphere is a quite complicated system with interactions with many different components. So this is the climate system, and of course you have processes that are acting at very different time and space scales. And of course, one of the questions is to know how predictable is this system. Okay, so when we are building a model, like a weather forecasting model, we are considering a certain number of processes, and we are building this model, and we consider that there are other processes that are weakly coupled to this one, and we let's say parameterize these different processes in a certain way. And of course we introduce in doing this we are introducing some model errors that are affecting the forecast. And this deterministic modeling approach induces certain model variability, which could be sometimes quite far from the real dynamics. And also another very important point is that in state-of-the-art weather forecasting systems, when we are looking at some forecast, usually we try to perform several forecasts starting from close initial conditions in order to have some information about the future skill of your forecast. And this is called ensemble forecast. And usually the plume defined by this ensemble forecast is quite small, and often the reality is out of this plume, and therefore we have too confident forecast in this case. So how can we correct for that? Well, people are using some ad hoc stochastic forcing to correct for that and to increase the variability of the models. But as it was shown by Catherine Nicolis, not the same one as the one mentioned before in the previous talk, Nicolis showed that it could have adverse effects on the climatological properties, because when you are introducing some stochastic noise, you can maybe improve the biases of your model, but you can degrade in a way other moments like the variability or other moments. So it was shown in the context of lower order system, and here the main question of the present talk is to see what happens when we are introducing stochastic forcings on what is the impact on the forecast. And I will do that in the context of a coupled ocean atmosphere model. So why using this type of model? Yes, of course, there is a growing interest in performing some long-term forecasting at seasonal, internal, and decadal timescales. And so this is the first reason. And the second reason is the fact that, well, when you have a coupled ocean atmosphere system, the ocean has a longer timescale than the atmosphere, so you can quite easily use the approach of stochastic averaging in order to define a reduced model for the ocean. So as I told you, there is a growing interest in performing long-term forecasts, and there are several evidences that decadal variability is indeed embedded in the ocean dynamics and also in the coupling between the ocean and the atmosphere. In particular, what we know is that there are very big oceanic gyres that are developing Here, this is the North Atlantic, and you have big gyres that are developing here, and that are at the origin, in particular, of the Gulf Stream, transporting heat here close to Europe there, and these are displaying low frequency variability on quite long time scales. And this behavior, in fact, has been also reproduced in the context of very simple low-order systems. These low-order systems were describing the dynamics of a fluid layer corresponding to the ocean, the upper layer of the ocean, and this dynamics was reproduced based just on wind stress forcings due to the atmosphere. So this is, I would say, this is dynamics associated with the coupling between the ocean, at least partly with the coupling between the ocean and the atmosphere. So what I would like to do is to start from a coupled ocean-atmosphere system, low order 1, and to then build, using stochastic averaging, to build a stochastic model for the ocean and look at its ability to predict the evolution of the ocean model. Okay, so this is the outline, and let us now start the discussion about how to build this type of coupled low-order systems. Well, there are already different models that were developed, and one interesting model was developed by Lawrence in '84. It was a model based starting from the primitive equations for the atmosphere, but with ocean corresponding just to a heat bath. So there's no dynamics in this ocean. And so we decided to develop our own low-order system based on two low-order systems that were already developed for the atmosphere and for the ocean. The first, so the atmospheric model is the one that was developed by Charney and Strauss, and then by Reynolds and Pierre Rambert, based on the quasi-geostrophic equations. And the ocean one was developed recently by Stefano Pirini for fluid layer describing the evolution of the upper layer of the ocean. Okay, so what are the pronostic variables I have in this system, describing the large-scale flows of the system? Well, this is just the stream function, so we will have a vorticity equation describing the dynamics in two layers in the atmospheric component. So this is the atmospheric component, and the temperature is related with the vertical variation of this stream function. And we'll have also a thermodynamic equation there, and then we have a fluid layer, and the upper layer of the ocean, which is above a quiescent deep layer. And to describe the dynamics there, we are using the shallow water equation. And of course, we need to couple these two systems. But before discussing that, just mentioning that we'll have a horizontal domain. It will be a rectangular domain of this form for the atmosphere and for the ocean. We'll have periodic boundary conditions for the atmosphere along the zonal direction, in the x direction, and we will have walls in the meridional direction, so you will have no flows through these walls, and this is a kind of channel at mid-latitude, in fact. And for the ocean, we will have a closed basin. We have walls on all the different sides there. And we fix the domain size to 5,000 kilometers in the y direction, and also some aspect ratio. We can play with this aspect ratio, and this is the ratio between the lengths in the y direction and x direction. well, I will not show any specific result. I will fix n to 1.5, in fact, here. Okay. And we need now to couple these two systems. So to do that, first we will introduce wind forcing to drive the ocean. And this is what I have written here. It will be introduced in the vorticity equation. So this is the curl of the wind stress. It will be introduced in the vorticity equation of the ocean. And we have also to introduce some coupling with the atmosphere. And, well, the easiest way, I would say, is to assume that the friction of the atmosphere, of the lower layer of the atmosphere above the ocean, the friction will be simply proportional to the velocity difference between, so this is the relative velocity as compared to the flow in the ocean. We also assume that the thermal forcing will be directly introduced in the atmosphere. Well, of course, radiation are coming from the sun, are entering entering partly in the atmosphere, but largely in the ocean, and this thermal forcing is then remitted through long-wave radiations toward the atmosphere. But we will assume that we have an instantaneous transfer of this energy toward the atmosphere. So we'll introduce this restoring force in the atmospheric thermodynamic equation toward a specific equilibrium given by this differences psi1 minus psi3 star corresponding to a certain temperature. In fact, this is proportional to the temperature. So this will be kept constant. Okay, so this is the equations. You have the vorticity equation of the upper layer of the atmosphere, vorticity equation for the lower layer of the atmosphere, and then the thermodynamic equation. And for the ocean, you have this the so-called reduced gravity quasi-geosophic shallow water equation, where we have introduced this so the curl of the wind stress. And h is represent, and it's quite important parameter, represent the depth of the oceanic layer, and rho the density of the fluid. Okay, so in order to develop this low order system, we have to develop the fields, the stream function fields in a series of orthogonal functions, and we have to truncate this series at a certain level, and we can take a look to well, this is the same approach as in Lorentz 63, or Salzman did that too in 62. And for the atmosphere, we'll keep, in fact, 10 different modes. Here, psi represent the mean vertical stream function, theta represent the difference between this stream function, and this corresponds to temperature, in fact. And we will also assume that we will have thermal forcing that will only depend on the latitude, that will be proportional just to the first mode that we will use. And for the ocean, we do the same, and we truncate the series of orthogonal functions to the 4 first modes. Just let me show you these different modes here. You have the 10 modes corresponding to the atmosphere, and in fact, well, Charney and Strauss used the 6 first modes here, and Reynolds and Pierre Humbert introduced these 4 additional modes that were called, and they called them synoptic scale mode because the wavelength is smaller. And here you have the modes corresponding to the ocean. Pirini has used 4 modes, and here it's important to note that we have an exponential function that is appearing here, and the purpose of this exponential function that was also introduced by Jiang and Gill in '95 is to allow for flow intensification on the western boundary of the closed basin, and this is typical of the dynamics of the gyres in the Atlantic, the North Atlantic Ocean. And well, we have a bit to take care because we are not using the same scalar product for both components. And if we do that, if we do this this program, we get two coupled systems, one with 16 variables, so a system of ordinary differential equations will have 16 variables or 24, and I will present only results for the 24 variable system. So we have several parameters in our problem here, but the main important parameters are first theta star, the thermal forcing introduced in the atmosphere, well, the aspect ratio, but I will not play with that. And you have also the coupling coefficient delta between the ocean and the atmosphere, and this is the term that is proportional to the forcing, the wind stress forcing introduced to induce the dynamics in the ocean. Okay, and clearly this is inversely proportional to the depth of this of the fluid layer. So let's look at the dynamics of this system. If I do not have any coupling between the ocean and the atmosphere, if h is tending to infinity, then I will not have any dynamics in the ocean, we will have a stable solution. But if we have value of delta, this is quite, well, quite reasonable in fact, you can get this kind of behavior. This is the time evolution of the coefficients of the four modes present in the ocean as a function of time, and time here is given in days, and this is about a 10-year integration here. And what you can see is that clearly you have a kind of decadal variability that is present there. Well, you have this kind of peaks appearing every, let's say, every 4 or 5 years. So clearly you have a dynamics that is quite slow for the ocean. Yeah, so this is an interesting property, and if we look at the variability in the atmosphere, it's much faster, and typically of the order of a few days. You have a very rapid variability for the atmosphere. And this is the typical structure in space of, so this is the mean field, in fact, associated with the stream function produced by the oceanic model. And what you can see is that there are developments of gyres, and much more intense when we increase the thermal forcing. You have clearly gyres that are appearing there. This is, yeah, that are appearing in that way. This gyre, it's a big gyre here. And this is typical to what we can see. Well, they are turning in the opposite direction as in the real system, but well, these double gyres are typical of what we can find in the North Atlantic and North Pacific. Okay, so let's look now at the polar spectra of this time series I have presented before. And this is here the the polar spectrum for the first atmospheric mode. And what you can see is that you have flat spectrum for small frequencies, and then a rapid decrease of this spectrum around, let's say, value of the frequency. This frequency is given in day -1 of the order of, let's say, a few days, let's say between here 10 to 30 days, and you have a decrease there. But the picture is very different for the ocean, and you have a kind of red spectrum for a very long domain of the frequency, and up to, let's say, frequency associated to a period of 6,000 days. So this is quite large, and it also indicates that you have a low frequency variability, as it was indicated in temporal evolution of the system. we can compute the Lyapunov exponent of this system. This is what I have done as a function of theta star, the thermal forcing. And this system displays periodic solutions. Well, the first stationary solution below 0.02. But just afterwards, just after that, you have periodic solutions. And then around 0.08, we have transition toward chaotic solutions, and we will have, for large values of the thermal forcing, we have about here 3 positive Lyapunov exponent, and even for larger you have 4. Here this is the number of positive Lyapunov exponent as a function of theta star, and clearly you have an increase of this number. And also here I have represented the Kolmogorov-Sinai entropy, which is steadily increasing here. So our system is chaotic for a certain set of value of the theta star. I have also to say that when you increase the coupling between the ocean and the atmosphere, we have an increase also of the amplitude of the smallest amplitude Lyapunov exponents, and this is quite counterintuitive, I would say. If you introduce an ocean which is quite relatively stable, and so it's forcing it's coupled to the atmosphere, so you could expect that, well, you will have a reduction of the instability, but it's not the case, and you increase the instability slightly. And if we look at the dynamics here, very close to the bifurcation here, you have a situation where when you increase delta from very small values to very large values, you increase the coupling, then you can go from periodic solutions to chaotic solutions. So this is also a bifurcation parameter. And we can compute the error growth in this context too, because we are interested in predictability of the system. And here I have represented the mean square error. Well, the experiments we are doing is just we have a reference solution, and we are of course always making some errors in the initial conditions. And so let's assume that we have an error at time t0, and we can look at the evolution of the system starting from this new initial condition, and assuming that we have a perfect model in the sense that we have so the model is corresponding exactly to the equations of the reference system, and then we can compute the mean square error evolution, and this is what I have done here. And here I have represented the mean square error evolution for the mean stream function. Here I use a log-log scale just to emphasize a bit what happens at the very beginning. And here this is for the for theta. This is for temperature. And what you can see is that we have a first slow decrease up to 1 day, and then a very, very rapid increase up to, let's say, 10 days, and then a saturation of the error. But the picture is very different for the ocean. You have quite stable situation, let's say, so the error is decreasing slightly up to 10 to 15 days. Then you have a rapid increase, and then you have a phase where you have a slow increase for about 1,000 days. This is quite long, and the error is behaving in this regime here, is behaving diffusively, and so this provides some hope to perform some long-term forecasting in this case. Okay, so let's now turn to the main question. So we have seen what are the properties of our coupled system, and we can now build a stochastic model for just for the ocean. So we will apply stochastic averaging that was developed by Arnold, and it was also nicely applied by Monahan and Kulina in 2011 on simple climate systems. So you assume that you have 2 components in your system. You have a slow component part, and you have a fast component part, and you are interested in predicting what happens for your slow components, and we can perform stochastic averaging. So what you are doing is to take the average of the velocity s for all the values y of the fast variable for a given value of x, and we do that if we do that, and if we have an infinite separation of timescales between the two components, then we end up with this equation, which is a deterministic equation describing the evolution of the slow variables. And Arnold named this approximation the A approximation. Now, clearly we are not dealing with a system with an infinite separation of timescales, so we have to add some stochastic forcing, and this is the n plus approximation that was proposed by Arnold, where Jx represent the noise-induced drift, and you have the Wiener process, so the stochastic forcing here, and sigma represents the variance, the standard deviation of this stochastic forcing. Okay, so and we can compute, in fact, this covariance matrix sigma square x as the integral of the correlation here. Correlation of what? Of the fluctuations of the velocity s as compared to the mean. We will assume furthermore that we will have an exponential decay of this covariance and of this correlation, sorry, and then we'll have to fit this psi value and look a bit at this covariance here. So let us apply that to the ocean. So this is the equations for my ocean. We have 4 ordinary differential equations. So this is the original equations, where F1, F2, F3, and F4 represent the wind forcings associated with the wind in the lower layer of the atmospheric system, of the atmospheric component. So the approximation is just the average of this one, because this is just there that we see the y variables, so the atmospheric variables. So we just take the average of the Fi to get the A approximation of the system, and then for the n plus approximation we have to look at the fluctuation f prime I, so Fi minus f bar I. The Fi represent these instantaneous values here. Okay, so what is the dependence of this the covariance function? So this is here the correlation function expressed as a exponentially decaying function, and we have adjusted this psi value, and we can also look a bit to what happens to this covariance matrix there. What is the dependence in the different variables of the ocean? Here I represented this covariance function for A2 and A4 for different entries of this covariance function, of this covariance matrix, sorry. And what you can see is that there are some dependence that are present, for instance here, but overall this is quite stable, I would say. It's quite constant as a function of A2 and A4. So as a first approximation, I will assume that this covariance matrix is does not depend on the variable of the ocean system. This is what I have done. And here you see the temporal evolution here of the n plus approximation and the output of the coupled systems. And clearly it's hard to see any difference. Well, the red one is, because I know it, the red one is the output of the coupled system, and the green one the n plus approximation. So clearly it seems that we have well reproduced the dynamics of the system. And if we look at the power spectrum, here this is for the for mode 1 of the coupled system, and here for mode 1 of the stochastic one. What you can see, well, the scale is not exactly the same. I should have changed that, but clearly we have a very good correspondence between the two spectra. So we have quite good model So we can ask the question, well, what is the ability of this stochastic model to predict my the ocean, the slow component of the system? So we have performed an experiment, a numerical experiment, in which we start from 1,000 realization along the reference system. So we start from 1,000 initial conditions selected on the reference system, and we perform an ensemble of 100 runs, starting from slightly different initial conditions on, around these different reference points on the attractor of the reference system. And we look at two quantities. The first one is we looked at the mean square error of the ensemble mean. So we take the mean of the ensemble, and we look at the difference. So the mean square difference between the observation, so the reference system, and the ensemble mean. We take the average of that, and in a way we take this ensemble mean as our forecast. And we can also compute the spread of the ensemble, so the variance of the ensemble around this ensemble mean. And this is what I have represented here. So the mean square error here for the ocean component. I have represented here the mean square error of the coupled system when there is no errors in the model, because when I'm building the stochastic averaging, I'm introducing in a way a model error. So the reference system when the system is perfect, the reference curve when the system is perfect is given by the red line here. The mean square of the ensemble mean when I have my stochastic ocean, and when I'm using the stochastic ocean, is given by the green points that are given here. The mean square of the ensemble mean when I'm using the deterministic ocean, so I remove the stochastic forcings, is given by the blue dots there. And clearly they are quite close to each other here, and therefore, after a short exponential error growth here, you have a kind of t-square evolution of the error before reaching a level, a stage where you have an error which is growing. The mean square error is growing as following a t evolution here. So you have two different phases, and this t-square evolution here is reminiscent to what we can find when we are looking at the dynamics of the model errors in deterministic systems. And the the second part is mainly diffusive. But what's interesting to note is that if we look at the variance of the spread, the variance of the ensemble of the stochastic ocean, you get this line here. That is, and this evolution is has a diffusive character, in fact, in time. So what is important to note here is that clearly the dynamics of the ensemble mean and of the ensemble spread are quite different. And what is important to note here is that if my observation is indistinguishable from one of the members of my ensemble, I should have a mean square evolution of the ensemble mean that should be equal to the variance around the ensemble. And clearly this is not the case. So, and in this case we say that we have a reliable ensemble forecast, but clearly for the short times we don't have this behavior. So clearly the forecast is over dispersive, so it's not very accurate up to 10 days, but after that is quite good. Now if we look at what happens for the when we use the deterministic system as our forecasting system, then we have a quite good evolution, I would say, of the ensemble mean, but the spread of this of the ensemble is decreasing, so all the trajectories are converging toward the mean, and therefore clearly in this case we have an under-dispersive, we qualify that as an under-dispersive ensemble forecast. Yeah, so this is the important point, I would say. For short times we do not have a good forecasting system, but clearly when we use the stochastic ocean, but clearly we have a good ensemble forecast for longer time scales. Yeah. So let me conclude. So we have developed a low-order coupled ocean-atmosphere system displaying well-separated time scales. Well, I didn't show that, but if we change the number of modes in the atmosphere, we can induce, instead of inducing double gyres in the ocean, we can induce single gyres. Clearly we have chaotic dynamics that is present in this coupled low-order ocean system for sufficiently large thermal forcings, and it also depends on the coupling. So we didn't find any, I would say, improvement of the quality of the forecast. Well, yeah, quality of the forecast of the atmosphere, or we didn't see an increase of the predictability time in the atmosphere in this context. We could hope to improve the quality of this predictability by coupling that with the ocean, but this is not the case. But clearly, the ocean has a quite long predictability time, in the sense that it reached the saturation of the error after about, let's say, 1,000 days, so after about a few years. We have performed stochastic modeling of this ocean, and it provides a quite good representation of the ocean component. But the aerodynamics of the ensemble mean is behaving mostly as a deterministic system for sufficiently small initial condition errors, and the ensemble variance of the ensemble is increasing diffusively in time in similar way as it was found by Secchi et al. For Orston-Uhlenbeck processes with additive noise. And clearly we have there an over-dispersion when we use that for short time scales, let's say up to 10 days for the weather time scales. And what we'd like to do in the future is to incorporate thermodynamic equation in the ocean and allow for energy flux, thermal fluxes between the ocean and the atmosphere. So this is the future, and in this case we hope to find some I would say we hope to find some decadal variability associated with this coupling in also in the atmospheric component. That's it. Thank you very much. Please. Yeah.
In your model, the equilibrium temperature is constant.
Yes.
But actually, this must has a seasonality.
Yes.
I mean, the response time scale of the ocean is definitely longer than seasonal. So if you input the seasonality in equilibrium temperature, the stochastic solution and the deterministic solution must be different.
Yes, right. But this is the first stage of the analysis. It could indeed introduce some sophistication, like introducing some seasonality in the thermal forcing. But before that, I would like to introduce thermodynamic in the ocean in order to really have, I would say, a better representation of the transfer of the heat fluxes between the ocean and the atmosphere, and then of course try to implement this seasonality too. Yeah.
And then I have to ask about the truncation. You chose 24 variables for deterministic system. Is there any specific reason for that?
Well, because the idea is really in the discussion that were at that time on the development of these models. First, there was this model by Charney and Strauss based on 12 variables. It was the starting point, and Reynolds and Pierre Rambert introduced 4 additional modes in order to see what is the impact on the structure, the underlying structure of the phase space of these 4 additional modes. These 4 additional modes were of synoptic kind scale modes with shorter wavelengths in order to see what happens in this context. And they have seen some differences in the phase space structure of the system. Yes, I could go further and add more and more modes, but at some point we have to stop and say, okay, let's focus on a low order system and look at the dynamics of this low order system. I could add more, but yeah, this is not the real purpose.
Maybe it's a similar comment or question. I mean, basically you have two coupled quasi-geostrophic models, more or less, right? And so you could just solve them numerically with decent resolution pretty straightforwardly, and then project that solution onto your 24 modes and see how many modes you need before the projection of the high order system starts onto a low order system looks like the low order equations, because if they're qualitatively different, then the low order system has nothing to do with the underlying equations. Right?
Yes, I agree with that. This is a good suggestion, but I didn't. The purpose was to have a quite simple tool and to use this simple tool to investigate other properties, like the application of different technique of averaging or application of other like data assimilation and different problems more related with the forecasting problem. Yeah. But I agree with you.
Is there any kind of fluctuation dissipation relation for your stochastic model? I mean, you had this exponential decaying correlation function, the fluctuations.
Yeah, I didn't look at that. It could be interesting to look at that.
Well, how did you? There's a term, capital G vex, in your N plus model. Can you maybe show the model?
Sorry?
The N plus model, I think it was called. Your stochastic. So you explained how this vector G.
Yeah, this is the noise-induced drift, this one.
How do you determine that?
I didn't, because I've computed, I have looked at the properties of this one, and this noise-induced drift will appear only if sigma is dependent on the variable themselves, on the A1 to A4. So this is a derivative of this sigma value, is proportional to the derivative of this sigma. So it disappears, in fact, when you have a sigma which is constant.
In your stochastic model, actually, when I saw the equation, it looks like you introduced the multiplicative noise.
Yes.
Of there, and then you chose Ito calculus.
Yes, but the point is that the sigma here is, this is, in general form, this is a multiplicative noise. But when I'm looking at the data, I have an additive noise.
In the case, how about choosing Stratonovich calculus? I think that might be reasonable, because your white noise is kind of approximation of a short time processes, which is definitely continuous.
Yeah.
But I think in the case, the Ito calculus is not consistent.
Yeah, I agree with you, but the point here is that it doesn't matter between Stratonovich or Ito calculus here, because sigma is constant. I used a sigma equal to constant.